Good day, I'm Norman Wildberger. In today's video, we want to move towards replacing classical propositional logic with a more powerful framework of the algebra of Boole. And what we're going to be looking at today in particular is replacing truth tables and Boolean equivalences in the reduction of propositional logic propositions via our algebra of Boole framework. So last time I gave you a very brief overview, an introduction to propositional logic, which roughly is concerned with real-life statements that happen to have truth values, whatever that means. True represented by T and false represented by F. Together with connectives and, or, not, implies, and equivalence. Okay, so that's the framework of propositional logic which attempts to systematize reasoning. Now, the algebra of Boole is a much more mathematically based orientation coming from Boole's original papers, suitably interpreted. So in the algebra of Boole, we work with vectors in a Boole algebra, B2 to the n. So we're thinking of vectors whose elements are 0 and 1, and the corresponding structure is given by addition and multiplication mod 2. And these are all component-wise operations. So arithmetically, the situation is very simple ultimately. And it's in this context that we want to embed propositional logic. So we are going to be thinking about taking this classical subject and embedding it inside the algebra of Boole. And this will be a very powerful thing for us. And it will have the effect that it really restructures the courses in philosophy departments and perhaps sometimes also in mathematics departments on propositional logic. So I'm going to be presenting a framework that really allows educators to really radically rethink this subject in exciting new ways and provides new opportunities for bringing more people into this actually quite interesting subject. So let me quickly review these connectives and how they're defined. We have basic propositions P and Q, and they have possible truth values of false or true in these various four combinations. And then here's the definition of P and Q, represented by this wedge. Here's the definition of P or Q, represented by the wedge in the opposite direction. And this is an inclusive OR, so it's true all the time unless both ingredients are false. On the other hand, this one is false all the time unless both ingredients are true. Then we have not P, which is just the negation of P. We have the implication P implies Q, which is always true, except when P is true and Q is false. The equivalence between P and Q, which is true when they are equal and false otherwise. And then we can also think about the constant propositions which are always false or always true. They are also useful. We just call them F and T. So this is the classical sort of starting point of propositional logic, these various connectives defined on propositions with truth values, true or false. Now, to move towards freeing the discussion from the philosophical trappings of meaning and subjectivity having to do with true and false, we are going to identify false with 0 and true with 1. So we want to recast the subject so it becomes an arithmetical subject, not a philosophical one. So we're going to disassociate the discussion from debates on the possible meanings or otherwise of true versus false. And we're no longer going to worry about the meanings of the atomic proposition. So we don't have to struggle with what exactly do these words mean. We just think about P and Q as atomic objects which can take on the values of 0 and 1. So now we're in the situation which the algebra of Boole exactly models for us. So now we're going to embed propositional logic, which I'll abbreviate with PL, not to be confused with the programming language of that name. We're going to embed this into the algebra of Boole. And so now, instead of having trues and falses, we have zeros and ones. But whenever you see a zero, you can think false. and a 1 you can think true if you want to, but you don't have to. Okay, here then are the various possible values for P and Q, the usual 0, 0, 0, 1, 1, 0, and 1, 1. And now here are the two basic arithmetical operations at the level of vectors in the Boole algebra: multiplication and addition. And they are just the mod 2 operations. We just take the product of these two elements, mod 2 for PQ, and we take the sum of them, mod 2, for P plus Q. So in the algebra Boole, these are the two primary operations, and all the other operations are defined in terms of them. This one notably is the exclusive OR with a 0 in this crucial spot, not a 1. If we want to recover the usual inclusive OR, then that's P plus Q plus PQ. So we actually take the sum of this one and this one, and we get 0, 1, 1, 1. Now, if we want to get at the implication, here is the Boole polynumber for that. P implies Q, what's usually called that. We are now going to think about it in the algebra Boole as 1 plus P plus PQ. Okay, so there's PQ, there's P. If you add them, you get 0, you add 1, you get 1. Add these, you get 0, add 1, you get 1. Here you get 1, add 1, you get 0. Here you get 0, add 1, you get 1. Right? So this indeed is an arithmetical description of what in the propositional logic story is called P implies Q. This one is the equivalence. 1 plus P plus Q. It's the negation of the addition. The addition is 1 precisely when the two things are not equal. This one then is 1 precisely when they are equal. And here is the negation of P expressed in the language of the algebra Boole. To negate something, we add 1 to it. So I'm going to now start thinking about these as the primary names and definitions of the operations in the algebra of Boole. And now if we want to make contact with the propositional logic story, we just have to connect the propositional logic connectives with the prior ones that are existing here already in our algebra of Boole framework. So P and Q is just the same as what we're calling P times Q. P or Q is the same as what we're calling P plus Q plus PQ. P implies Q, that's the same as this one. P equivalent to Q is the same as this one, and not P is the same as this one. So this way we can embed our 5 basic propositions inside the algebra of Boole. You might say, what about this one here? There's a gap here. And we could fill this gap by combining these ones in various ways. Maybe the most obvious thing to do is to take this one and just negate it. So in the propositional logic story, the exclusive OR could be described as not P is equivalent to Q. But I'm going to leave it empty because it's not actually sort of primary in this story. Now, I at the same time want to connect it with our Boolean algebra story, okay, where also we have a slight variation from the algebra of Boole. Notably, instead of having this sum, we have our circle sum, P circle sum Q, which is our name for the inclusive OR. So in the Boolean algebra story that we've already talked a lot about, the main operations are the multiplication, the circle sum, and the negation, which is with a bar over it. And here, just to sort of complete our story, here are the circuit diagram representations of these various things. There's the AND gate, it's represented by this column. Here's the XOR gate, that's that operation. Here's the OR gate. Here's the negation of the XOR, which is the XNOR. Has a little circle there representing the negation. And this is just the inversion or the NOT operation. So we are with the algebra of Boole, having a framework that can easily incorporate propositional logic by making these associations, can easily incorporate the Boolean algebra by having these associations, and naturally connects with the usual circuit diagram story by giving algebraic representations of these basic gates. Okay, so that's the basic framework, and now the idea is simply that we want to deal with questions, say, in propositional logic. We just convert everything to the more fundamental level of the algebra of Boole and perform all the calculations there, which is just grade 9 polynomial algebra, simplified because everything is mod 2. So we're going to look at a couple of examples here in detail to compare how things look like in these various frameworks. So we're going to start off with the non-obvious distributive law, which is this one here. P or Q and R is equivalent to P or Q and P or R. So to convince ourselves that, first of all, this is true, we can create a truth table. So this is a very powerful and sort of basic technique that we learn to verify the validity or otherwise of some statement like this. So here are P, Q, and R, the various inputs. Here are the usual 8 possible ways of assigning trues and falses to them. And here then we're going to assign values to these various ingredients in here. So I've copied P. Here is Q and R. So Q and R, we're just looking at those and we're taking an and. So there's a false here. These are all false. This one's true. There's a false, 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 and here there's a true. Okay, so that's that one there. And then P or Q, that's there, that's an or. So there's an F, and the rest are T's because there's at least a true there somewhere. And here's another or, P or R now, these two. And that's going to be false here, true there, false here because there's two falses, true there, and true for the other ones. Okay, so now let's continue this. We're not finished yet. I will now have a look at this left-hand side where we need to compare the value of P with the value of this little term here. And they're connected with an or. So F or F. Well, that's F. F or F is F. F or F is F. F or T is T. T or F is T. 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 If we have at least one T, it's T. Over here, we have to connect these two with an and. So we're usually going to get an F unless they're both true. So we get F, F, F. Here they're both true, both true, both true, both true, both true. Now if we look at this stage here, at this term, which is represented by this intermediate column in blue, and this whole term represented by this intermediate column in blue, we see that those two columns are the same. That's telling us that these two propositions are equivalent. They always have the same truth values. Now, if we want to do that more formally, what we could actually do is actually put the equivalence in here and now treat it as a single expression and evaluate the truth or falseness of this single expression. To do that, we would have to compare, for every line, the net value of this thing, which is the blue over here, with the net value of this thing, and see whether they're equivalent or not. Is false equivalent to false? That's true. FF, true. FF, true. True, true, true. True, true, true. And also, these are all true also. The net result is that the whole thing is represented by this column of truths. That means that this statement is always true independent of the inputs. So this is a tautology. That's our favorite kind of expression. It's always true. You can always depend on it. And it gives us then a powerful mechanism because we know now that we can replace this with this expression because they're equivalent. So this is the truth table point of view or technology to verify the truth of this expression. Let's have a look at the same identity from the point of view of simplifying it using Boolean identities. Now, unfortunately, this is a very fundamental one, so it itself is already usually considered a fundamental Boole identity. And it's not so easy to verify it by other Boolean identities. So that actually doesn't get us very far because of the actual fundamental nature of this thing. So now let's switch to the algebra of Boole, where we have to try to recast this thing. So let me remind you how you convert. So the and here is represented just by multiplication, product. So this is represented by QR. And this or here is a circle sum. Here there's an or, that's a circle sum. Here there's an or, that's a circle sum. And this and is just a product. So this is, well, along the way of becoming an algebra of Boole expression. It's still not in sort of primary algebra of Boole form because it has these circle sums in it. So our next stage now is to actually prove this thing. This is an identity in the algebra of Boole. We want to establish this identity. So let's have a look at the left-hand side. P circle sum QR. How do you do a circle sum in the algebra of Boole? You take the first one, you add the second one, and then you add the product. So you get P plus QR plus PQR. Let's circle that. Okay, that's the left-hand side. Now let's look at the right-hand side. P circle sum Q times P circle sum R. There's P circle sum Q. P plus Q plus PQ. And here is P circle sum R. P plus R plus PR. We now have to multiply these things out. So we'll multiply all of these by P. So P times P is P, P times R is PR, and P times this PR is another PR. Now we multiply all of them by Q. We get QP plus QR plus QPR. And now we multiply all of them by P times Q. So we get PQ plus PQR plus the product of these is another PQR. Okay, now we simplify. And there's some cancellations. For example, these two will cancel. This QP will cancel with that PQ. These two guys will cancel. And we're left with P plus QR plus QPR, which is the same as PQR. So that's the result of the right-hand side. The left-hand side equals the right-hand side. These two Boole polynumbers are the same. That's the meaning of the equivalence in the algebra of Boole. It just means that the two expressions as Boole polynumbers are equal. Equivalence is just equality of Boole polynumbers. For our next example, let's look at transitivity of implication, which is this statement here, that P implies Q and Q implies R. That implies that P implies R. If P implies Q and Q implies R, then P implies R. That's the meaning of this statement. So a truth table approach is surefire. PQR, the 8 various possibilities. Here is the implication P implies Q. I remind you the implication is usually true. It's only false when the first one is true and the second one is false. So let's just go through here. False implies false, true. False implies false, true. False implies true. Whenever the first one is false, it's automatically true. But here we have true implies false. That's false. True implies false, false. True implies true, true, and true. Okay, similarly, Q implies R. We're just going through these ones, you can check. And P implies R. We're going through these two, and you can check. Okay, so now let's sort of complete the story. We now connect these two with this and. T and T is true. Remember, an and is true only if both of them are true. So this is true. True and false, that's false. True and true, that's true. False and true, false. False, if there's a false, it's false. There's another true. Okay, now let's have a look at this left-hand side and the right-hand side. True, true, false, true, false, 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 true. That's not quite the same as the right-hand side. They're not the same. But we're not saying that they're the same. We're saying that this one implies that one. So we're going to finish the story by putting in the missing connective, the fact that this implies this, and now we're going to evaluate whether these guys actually do imply these ones. Does true imply true? That's true. True implies true, true. False implies true, true. True implies true, true. False implies false, that's true. False implies true, true. False implies false, true. True implies true, true. Remember, an implication is only false if you have true implying false, and we don't have any of those particular combinations. So, we see that happily we get a whole bunch of truths. So the entire expression is always true, or it's a tautology, the happiest situation. So this is then a rule that's always valid no matter what the inputs are. So it's dependable. We can use it then in general without worrying about, is it perhaps not true in some special situation. This one's always true. Now in this case, it's also possible to prove this result, establish it, by using replacements or equivalences coming from our Boolean identities. And on the web I've found some examples of that, and they're actually quite complicated. And almost too complicated for me to happily describe them. So here is a version, a proof, which kind of mixes Boolean identities with a few sort of inference rules, okay? But you'll get the idea. So I want to first of all point out that this particular result that we've been looking at has another name. It's sometimes called hypothetical syllogism. And it can be re-expressed in terms of this kind of standard format. This is very important kind of format in propositional logic, where we have a number of statements which are written on top of each other, and then there's a bar, and underneath it is a conclusion. The interpretation is that these statements on top of the bar are the premises. So we're supposed to assume the truth of those and conclude the conclusion. So P implies Q and Q implies R. If we assume those two things, then hopefully we can conclude that P implies R. So let me give you actually the proof from Wikipedia, which you can check. So this is the proof that's found there of this hypothetical syllogism. And we're not going to go through it in any detail. I just want you to see it. Okay, I want you to see what kind of form it has. So we start with this. P implies Q and Q implies R. And stated that this is the given. So this is like the assumption. This is where we're starting. We're starting with this, and hopefully we're going to have a whole bunch of deductions, and hopefully at the end of it, this will be one of the conclusions that we come to. That's the scope of the argument. Okay, what do? Well, we convert these implications to something called material implication. P implies Q is converted to not P or Q. Q implies R is converted to not Q or R. So when we actually get working, we want to get rid of the implications, replace them with ands and ors and negations. Okay, and now we replace this with this using the distributive property, because here there's an and here there's an or, and so you can think of this thing and the not Q, or this thing and the R. And then the next step from here is to go to this step. That's something called conjunction elimination. But we have to keep going. Okay, and then the next step is to convert what we just had to this expression via distributive law. And then we go from here to here using the law of non-contradiction. So there's some law there that we're using. And then we go from here to here using a disjunctive syllogism, some other rule. And then from here to here, conjunction elimination. And then another one, we sort of convert back to what we eventually want, to the P implies R. That's called material implication again. So I'm not going to go over the details here, okay, because we haven't actually discussed all these various techniques. But the point I want to emphasize is that if you're taking a propositional logic course, this is the kind of thing that you have to learn. You have to learn these various steps or techniques that allow you to simplify things. And exactly which one you should use at any given stage is often not obvious. You have to kind of, it's like in a maze, you kind of turn left or right, or maybe try this or try that, and hopefully you will progress towards something simpler. But if you have something that's very complicated to start out with, well, it's very easy to get lost in this maze. So I actually took a course in propositional logic when I was an undergraduate at the University of Toronto many years ago. And it was a philosophy course, and it was a kind of an easy course because as a mathematics major, this topic is pretty easy. But still it was kind of pleasant. But I do remember we had to spend, quite a bit of time to, get your head around these various rules and then apply them reasonably consistently and correctly. So the conclusion then is that we've started with this as the given, and we've managed to use some deductions to get this thing here. And so then we're allowed to deduce that this whole thing over here implies this thing here. So this is a proof from Wikipedia. So well and good, but my point is that we are going to avoid all of this. Right? So the reason I'm not going through this in any detail is because I don't want you to learn any of it. Really, I don't. I want you to appreciate that we can dispense with this entire technology. It's a very powerful but maybe unnerving claim. So let's see how that works with this example. So we're going to evaluate this thing using the algebra of Boole. Here is the expression that we're interested in. P implies Q and Q implies R, all of that implies P implies R. And what we're going to do with this thing is we are going to evaluate it. That's what we're going to do. We're taking this expression and we're finding out what it's equal to. So this is just a question of simplification and reduction. So we have to, first of all, convert everything, perhaps in some steps, but ultimately to the algebra of Boole notation, which ultimately only involves additions and multiplications and possibly the number 1 in various places. Okay, so P implies Q. We know that's equal to 1 plus P plus PQ. That's how you write the implication in the algebra of Boole. P implies Q equals 1 plus P plus PQ. Here is Q implies R. That's equal to 1 plus Q plus QR. And this and here is just multiplication. So that's the left-hand side. Over here, we have 1 plus P plus PR. And I'm still just leaving this implication here temporarily for now, because I want to simplify this left-hand side. So we're going to expand it out. So let's see what happens. So 1 times all this, 1 plus Q plus QR, P times all of it, P plus PQ plus PQR, and PQ times all of it, PQ plus another PQ plus PQR. I'm using the fact that Q squared equals Q without explicitly saying it. You all know that by now. Okay, and that's the left-hand side, but still that implies 1 plus P plus PR. So we've just simplified it by expanding out. Now there's some cancellations here. Let me see if I can point them out. So there's a 1, there's a P, there's a Q, there's a PQ. So I guess the Q, these PQs cancel. These two cancel, let's say. We still have another PQ over here. We have a QR, and these two PQRs cancel. Okay, so we're just having 1 plus P plus Q plus QR plus PQ. those are the things that did not cancel, implies 1 plus P plus PR. Now we're going to evaluate that. We're again using the fact that we can express an implication in the algebra rule as the first term, actually 1 plus the first term plus the product of this thing times this thing. Okay, so when we expand this out, what do we get? The 1 plus 1 disappears. We get a P plus Q plus PQ plus QR, okay? And now when we expand this out, what do we get? Well, let's think about this 1 plus P times this 1 plus P. We multiply them together, we're just going to get 1 plus P squared, which is just 1 plus P, okay? So I multiplied this times this. And now I'm still multiplying this thing here, Q plus PQ plus QR, times 1 plus P. Okay, so there. And now I still have to multiply everything by PR. So what do we get there? PR. So if I multiply PR with times 1, I get PR. If I multiply it by P, I get another PR. They'll cancel. That's good. If I multiply here, I get PRQ. And I multiply by here, I also get another PRQ, so they'll cancel, and I'll have one last thing, which is another PQR or QPR. So we've gone from here to here. We still have a bit more expansion to do. All right, so carrying on from that, I've just copied what I had on the last line of the last slide. So let's have a look if we can simplify this. There's a 1 here. The 2 P's will cancel. Maybe I should... Okay, so the 1s will go there. This P and this P will cancel, all right? There'll be a Q, there'll be a PQ, there'll be a QR, fine. And what do we get when we expand this out? We get, what are you getting? Q plus QP, and then this P times 1, P times P, that's 0. And we'll also have QR times 1 plus QR times P, with another QPR at the back. And now what happens? This Q and this Q cancel. This PQ cancels with that QP. This QR cancels with that QR. And this QRP cancels with that QPR. And the total effect is 1. What have we done? We have evaluated the original expression. We've evaluated it. It's been a computation. And the result is that this is the Boole Pauli number for that thing. What does that tell us? It tells us that as a Boole function, this is just the function 1. Or in the propositional logic story, it's always true. So this is a tautology. Okay, a Boolean function which is always 1 is the equivalent of a propositional logic tautology. So we have proved what we want to prove using just grade 9 algebra simplified. Okay, this is it's just fabulous. It really shows that the algebra of Boole rules. It just subsumes the existing technology for propositional logic. And this would become even clearer if we looked at some more complicated examples. So if you imagine some bigger identity involving, say, 5 or 6 different variables, making a truth table is going to involve 32 lines or 64 lines or maybe more. It's a huge amount of work. Okay, figuring out how to simplify it using clever combinations of Boolean expressions. Now we use the distributive law on this, and then we absorption here, and some identity here, and some other syllogism here. And maybe it'll simplify it. Oh no, we've done it wrong. Blah blah blah. Huge amount of work. What we're saying is, with the algebra of Boole, just get a grade 9 student. Please evaluate this thing. Maybe there will be some long expansions that have to be done, but fortunately we have the Boole reductions to help us there. Whenever we get 2 of anything, it's 0. Whenever we get a power bigger than 2, we just rub off that power. Our computers in particular can do that kind of computation in a flash, even with huge polynomials. Okay, so it's very powerful. So I'm going to carry on in this direction with the third aspect of propositional logic, which we haven't talked about too much yet, which are the rules of inference. Okay, and how, not surprisingly, the algebra of Boole manages to transcend those as well. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.